Hi everyone. Today we'll learn how to apply L'Hopital's rule to indeterminate powers. Let's start by computing this limit. If you would like to compute this limit on your own, stop this video and download these notes using the link in the video description. This is one of the limits we computed in the previous video. If you haven't watched that video, I will add the link in the video description. I will go through the computations quickly. First, I rewrite the expression so that it is of the form that allows me to use L'Hopital rule. I will rewrite this as ln of x divided by 1 over x. Now, the numerator goes to negative infinity. The denominator goes to infinity, which allows me to apply L'Hopital rule. And I get the limit as x goes to 0 from the right side of the derivative of ln of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. I can simplify this expression and I get the limit as x goes to 0 from the right side of 1 over x times negative x squared. Dividing by 1 over x squared is the same thing as multiplying by x squared. Now a few x's cancel and I get the limit as x goes to 0 from the right side of simply negative x. I now plug in 0 and I get 0. This limit is 0. Let's see if we can apply a slightly different technique to compute the limit of the expression x to the power of x. I will show you two ways of computing that limit. Here's the first one. The first method says, first write your function as y. You may want to compute the limit of this expression. Note that you cannot simply plug in 0 to this expression because this 0 to any power should be 0. So as x's get closer and closer to 0, that x in the base is trying to make the entire expression 0. However, as x's get closer and closer to 0, the exponent gets closer and closer to 0. And we know that anything to the power of 0 should be 1. So the exponent is trying to make this expression 1. The base is trying to make this expression 0. It's not clear what exactly this limit is. This limit is of the form 0 to the power of 0, which is an indeterminate form. Here's how the first method goes. First, name your function by y. The goal is to find the limit of y as x goes to 0 from the right. Then, apply natural logs on both sides. This will allow you to take this exponent and move it in front of ln by the properties of natural logs. So this gives you ln of y equals x ln of x. Your goal is to find the limit, so now I will take the limit as x goes to 0 from the right side on both sides of this equation. And I will get the limit as x goes to 0 from the right of ln of y, that will equal the limit as x goes to 0 from the right of x ln of x. I believe we know the value on the right side. This limit we computed in the first exercise today, and we computed that that limit was 0. So the right side of this equation is 0. What's more, natural log is a continuous function. And continuous functions have one special property. You can take the limit and move them inside of ln. So this is the same thing as ln of the limit as x goes to 0 from the right side of y, and that equals to 0. And I was able to move that limit again inside of ln because ln is a continuous function. I wanted to move the limit inside because my goal is not to find the limit of ln. My goal is to find the limit of y, the limit of this expression. How can I get rid of ln? Well, I will say that e to the left side of this equation equals e to the right side of this equation. And I will get e to the power ln of limit as x goes to 0 from the right side of y equals e to the 0th power. E and ln cancel each other because e and ln are inverse functions. So that gives you the limit of y as x goes to 0 from the right of y equals 1. So the answer of this limit is 1. I told you I was going to give you a second way of computing this limit. Here is the second way. I want to compute the limit as x goes to 0 from the right of x to the power of x. I will rewrite this expression in the following way. I will write it as the limit as x goes to 0 from the right of e to the power of ln x to the power of x. These two expressions are the same because, as we know, e and ln are inverses of each other. So e, whenever you have e, ln of anything, that is the same thing as that anything, which means that e ln of x to the power of x is the same thing as x to the power of x. That's why I was able to replace this with this. I do so now because according to the limit laws of logarithms, I can take this x and move it in front of ln. And I get the limit as x goes to 0 from the right side of e x ln of x. What's more, e to the exponent of x is a continuous function. E to some power is a continuous function, which allows me to move the limit inside of that continuous function. So I will move it into the exponent. By continuity of the exponential function, this is the same thing as e to the limit as x goes to 0 from the right side of x ln of x. We already know the value of this limit. The value of this limit is 0. So this is the same thing as e to the 0th power, which is 1. I have two problems for us to try. In one of them, I will use method 2. In one of them, I will use method 1. In the next example, we must find the limit of, as x goes to infinity, of x to the power 1 over x. Note that if you are going to plug in infinity, this will be of the form infinity to the power of 0, which is an indeterminate form. Let me here use the second method. So I will rewrite this limit as the limit as x goes to infinity of e to the power ln of x to the power 1 over x. Now I will do two steps at once. I will take this 1 over x in front of ln, and I will move the limit in the exponent of e. And I will get e to the limit as x goes to infinity of 1 over x ln of x. Now, I think I can compute this. I get e limit x goes to infinity, and let me rewrite this so that you see what I can do here. I can write it as ln of x divided by x. I believe now, to compute this limit, I can use L'Hopital rule. Ln of x as x goes to infinity goes to infinity. X as x goes to infinity goes to infinity. This is of the form infinity divided by infinity. I will apply L'Hopital rule. So I get e limit as x goes to infinity. And let me remind you that I'm using L'Hopital rule here in the exponent. And I will get in the exponent 1 over x. In the denominator, the derivative of x is just 1. So that is 1 over x. The limit of 1 over x as x goes to infinity is 0. So this is the same thing as e to the 0th power. The limit of 1 over x as x goes to infinity is 0. Because as x gets bigger, the whole thing gets smaller and smaller. E to the 0 is 1, so this limit is 1. Let me show you one more example. This time I will use method number 1. When I plug in infinity to this expression, the parentheses gets closer and closer to 1, and the exponent gets closer and closer to infinity. This is of the form 1 to the power of infinity, which is also an indeterminate form. Let's try to find this limit. I use the second method this time. I will say y equal the function that we are trying to find the limit of. So y equals 1 plus 3 over x to the power of x. Then I take natural log on both sides. Then the exponent comes down. Then I take the limit on both sides as x goes to infinity. So I take the limit as x goes to infinity of ln of y. That will give me the limit as x goes to infinity of the right side, x ln of 1 plus 3 over x. As x goes to infinity, this goes to infinity, and here I get closer and closer to 0, so I get closer and closer to ln of 1, and ln of 1 is 0. So this is of the form infinity times 0, indeterminate form. To apply L'Hopital rule to the right side, I have to rewrite this expression. So now I will work only on the right side. I will rewrite this expression first as ln of 1 over plus 3 over x divided by 1 over x. This is in a much better form now, because this is of the form in the numerator I get 0, in the denominator I also get 0. This is of the form 0 divided by 0, which allows me to use L'Hopital rule. And I get the limit as x goes to infinity. Take the derivative in the numerator. Using the chain rule, I get negative 3 divided by x squared times, and the derivative of ln is 1 over whatever was inside of ln. The derivative in the denominator is negative 1 over x squared. Few things cancel. I can move this 3 right here. And this will be negative 1 over x squared. This is negative 1 over x squared. I could cancel those. So that leaves me with the limit as x goes to infinity of 1 divided by, or rather 3 divided by, that 3 was there, 3 divided by 1 plus 3 over x. What happens to this expression as x goes to infinity? As x goes to infinity, this gets closer and closer to 0. So this is 3 divided by 1, which is 3. So the right side was 3. What was the left side? By continuity of ln, I can move limit inside of ln. So that equals ln of the limit of y as x goes to infinity. I take e to the left side equals e to the right side. When I do it on the left side, e and ln will cancel. So I will get on the left side the limit as x goes to infinity of y. On the right side, I will get e to the third power. So this limit is e to the third power.